Hey gang, welcome to the third video for AP Statistics. Today we're going to talk about how do we describe quantitative data with numbers. Last video was all about how do we describe it with graphs. This one is how do we do it with numbers. But we're going to start off with a little graph. We're going to talk about a box plot. Now last video we talked about stem plots and dot plots and histograms. Why would we use a box plot if we have those other choices to us? Well, first of all, box plots are super easy, very easy to construct. Secondly, they do a great job of handling outliers. They do a much better job of handling outliers than any of the other ones. And they're great for us to use with medium or large data sets. If we have a large data set, a box plot can be much, much easier than drawing a histogram for that thing. Disadvantages of box plots. Well, first, you can't see the individual observations. So they're kind of like a histogram in that regard. And secondly, you definitely should not use a box plot if you're using a small data set. If your sample size is less than 10, that's what n is, a sample size, a box plot is not going to do you much good. So those are two of the disadvantages. How do we construct a box plot? Well, another name for a box plot is a 5-number summary. So in order to construct a box plot, you need to find the 5 numbers. The 5 numbers that we use to build a box plot are, first, the minimum, next, quartile 1, then the median, then quartile 3, and then the maximum. Those are the 5 numbers. So when you hear me refer to a 5-number summary, I'm talking about these 5 numbers. You draw the box from Q1 to Q3. That's why it's called a box plot, because it has a box in it, and the box goes from Q1 to Q3. The median is the center line, right down the center of the box, and then the whiskers, you may have heard these referred to as box and whisker plots. The whiskers go from the minimum up to the box, and then from the box up to the maximum. So let's take a look at one. So here's our box from Q1 to Q3. You need to determine outliers. Box plots do a great job of evaluating and showing outliers. So you need to be able to figure out what those outliers are. There's a name for the box. It's called the interquartile range, IQR. It is the range, the length of the box. The formula is Q3 minus Q1. You should write that down. IQR equals Q3 minus Q1. That's going to be an important thing that we use a lot. Next, to determine an outlier, here's the first formula. This is the formula for the lower outliers. You do Q1 minus 1.5 times the IQR, and you calculate a number for that, and that number then would be what we call the lower fence, which is the dotted line. The upper fence is Q3 plus 1.5 times the IQR, and you use that then to construct the upper fence. Any observation that's outside of that fence is considered an outlier, and we would put a dot for those outliers. The whisker would go from the quartiles, from Q1 and Q3, up to the biggest or smallest observation that is within the fence. So whatever the first observation is that's within the fence, that's where the whisker would stop, and then the outliers would just have dots on the outside. So here's a typical test question. Evidence suggests that a high indoor radon concentration might be linked to the development of childhood cancers. So we have 2 samples. I'm going to give you 2 samples. The first sample consisted of houses in which a child was diagnosed with cancer, and the second sample has no recorded cases. And then I would ask you to create the box plots and then compare the distributions. That's a very typical question. So I would give you the data sets and you would be asked to construct the box plots. I did that part for you. So here's the box plots. You can see lots of outliers on this one, 2 different sets. This is what we call a side-by-side box plot. So there you can see and you can compare them very quickly to each other. Now we do have to compare them. So you're going to write a short little paragraph to compare them. Remember from the last video, anytime you're asked to compare a distribution, I want you to cuss and I want you to be specific. So we want to talk about the center. The median radon concentration for the no cancer group is lower than the median for the cancer group. There you're talking about the center. And you're being specific, radon concentration. Next, we want to talk about the spread. The range of the cancer group is larger than the range for the no cancer group. Finally, next we want to talk about the shape. Both of the distributions are skewed to the right. And finally, we want to talk about anything unusual. The cancer group has outliers at 39, 45, and so on. The no cancer group has outliers at 55 and 85. So center, shape, spread, anything unusual, and we want to be specific. So that's the perfect description for this particular two parallel box plots. Now, measures of central tendency. If we're talking about the center of a data set, we want to talk about the median, which would be the middle of the data, the 50th percentile, 50% above, 50% below. It helps if the observations are in numerical order. So one of the first things we want to do when we have a data set is put those in order. Another measure of central tendency is the mean. That's the average. This is where you add them all up and you divide by how many there are. We use this symbol mu to represent a population mean, and we use x bar, which is that symbol, to represent a sample mean. You're going to get very familiar with those two symbols. Here's the formula. X bar is equal to the sum. That little Greek symbol E is the capital Greek letter sigma. It means to sum the values that follow. So you take the sum of all the x's and you divide by how many there are. That's your basic average that you've been doing since 4th grade or 3rd grade, whenever you first did averages. Another measure of central tendency is the mode. It's the observation that occurs the most. Very easy. There can be more than one mode. If all the values occur only once, then we say there is no mode. Right? So that's also a possibility. So when we're talking about center, we're talking about the mean, the median, and the mode. We don't use the mode as often. Here's an example. Suppose we are interested in the number of lollipops that are bought at a certain store. We take a sample of 5 customers and we have the following number of lollipops. We want to find the mean. Well, the numbers are in order and n is odd. So we want to find the middle observation. 2, 8, there it is. That's the median, the number in the middle. What if I add an extra one? What if I have 6 lollipops? Well, now, since I have 6 customers, the numbers are in order, but n is even. So if we count down, 2 and 12 are matched up, the 8 and 3 are matched up, the 4 and the 6 are matched up, we have to find the middle between those two. We have to find the number that's directly in the middle between 4 and 6. So the median would be 5. Now, what about the mean? Same 6 customers, we want to find the mean. Find the mean, we add them all up and we divide by n. So we do 2 plus 3 plus 4 plus 6 plus 8 plus 12. We divide that all by 6 customers, and we get the mean to be 5.833. And that's the way you label it, x bar. That's the mean of the sample. What happens to the median and the mean if the 12 lollipops were 20? What if we notice that I changed the 12 at the end to 20? Well, the median, 2, 3, 4. Guess what? The median is still 5. It hasn't changed. But the mean, if we add them all up and divide by 6, the mean is now 7.17. So it went up. It was 5.8. Now 7.17. What happened? Well, let's do another one. What if it was 50 instead of 20? Notice that I changed it to 50. The median, again, going to count in, same way I did before. Median is still 5. The mean, however, add them all up, divide by 6. Well, now the mean suddenly 12.17. Again, what happened? The median stayed the same, but the mean went up. There's a name for that, and it is called resistant. Resistant statistics are ones that are not affected by outliers. So the median is resistant. The median didn't change. It was not affected by the outlier. So yes, the median is resistant. Is the mean? No, the mean changed. When we changed to 50, it got a lot bigger. So definitely something you want to write down and take a note of. Let's look at another data set. We want to find the mean. Add them all up. I did it for you. Add them all up, divide by, how many are there? 8. I got 25.5. We want to find out how each observation deviates from the mean. In other words, how far off does each one go? So I would do 22 minus 25.5. Then I would do 23 minus 25.5. Then I would do 24 minus 25.5 and 25 minus 25.5 and so on, and add those all up. This is called the deviation from the mean, and it's 0. Is it always going to equal 0? Yes, it is always going to equal 0 because that's the mean. That's one of the characteristics of the mean. The mean is one of the centers, and if you subtract You're always going to get 0 when you add them up. Let's look at the following data set. This is a bigger data set. We want to find the mean and the median. So we're going to create a histogram, and we want to find the mean and the median. So here's our histogram. They are in order. So the median is right in the middle. It's going to be 27. And the mean is also 27. I added them all up and I divided by, how many are there? 2, 4, 6, 8, 10. There's 20 of them. So I did that for you. Look at the placement of the mean and the median. They're the same, right? They're right in the middle. This is a characteristic of a symmetrical distribution. When you have a symmetrical distribution, the mean and the median are going to be right in the center. Now here I changed it. Now I have a different type of histogram. Looks like that. That's no longer symmetrical. Now let's calculate the mean and the median for you. Here's the median. Here's the mean. Notice that the mean is bigger than the median in this case. Interesting. In a symmetrical one, they were the same, but in a skewed one, the mean's bigger. Look at that placement. Let's do one more. Totally different data set. This time create a histogram. This is what this histogram looks like. Now we're skewed to the left. Let me show you the median and the mean. Again, look at that placement. So what's happening in a skewed distribution? Interesting. Let's recap. In a symmetrical distribution, the mean and the median are equal. In a skewed distribution, the mean is going to be pulled in the direction of the skew. So in a symmetrical distribution, you should always report the mean. If I give you a symmetrical distribution and I ask you to describe it, you want to talk about the mean. But in a skewed distribution, you don't want to talk about the mean. You want to talk about the median. Because remember, the median is resistant to the outliers and the mean is not. We want to talk about the median in a skewed distribution.
That's all, folks.